Imagine the laws of physics not as rules governing matter, but as lines of code running on a universal processor. Recent theoretical work and experiments strengthen the case that information is conserved in quantum processes, one major clue in the black hole information debate, though the story is still developing. In 2025, researchers studying entanglement argued that preservation of information could even help explain cosmic mysteries like dark energy, not as a hidden force, but as the operating cost of computation itself. If that's true, then understanding matter and energy means starting with something deeper: information. From atoms to bits, the new foundation of reality. For most of human history, reality was explained in tangible terms, things we could touch, weigh, and observe. Rocks, rivers, stars, and fire all seem to fit into a framework of matter and energy shifting from one form to another. This machine-like picture of the world guided centuries of science and engineering. But over the last several decades, a new perspective has gained ground, one that sees the underlying fabric of reality not in terms of objects or energy, but in terms of information. At first glance, information seems abstract, even out of place in physics. Most people think of files on a computer or numbers on a page. In physics, though, the word carries a stricter meaning. Information is the quantifiable set of distinctions between possible states. It defines how systems evolve, how particles interact, and even how large-scale structures emerge in the universe. Many physicists now argue that information is not just a tool for describing physical processes, but a foundational quantity, on par with matter and energy. One of the most concise ways this idea has been expressed is in John Wheeler's phrase "it from bit." Wheeler, one of the leading physicists of the 20th century, suggested that everything physical, from particles to fields to the very geometry of spacetime, may ultimately arise from binary distinctions, the yes or no decisions that form the logic of computation. When he first introduced the idea, it sounded speculative. Yet today, with advances in both quantum theory and information theory, the notion that reality might be grounded in bits looks far less like a metaphor and more like a serious framework for physics. To see why, consider how modern physics treats information. Unlike mass or energy, information might seem intangible, yet it too can be measured. And in processes governed by quantum mechanics, it appears to follow strict laws. For instance, in entanglement, two particles that are linked across space always keep their informational content balanced, even as they shift states. The individual states may change, but the total information describing the system doesn't disappear. This conservation suggests that information, like energy, must be accounted for everywhere in the universe. This principle shows up in some of physics' thorniest problems. Perhaps the most famous example is the black hole information paradox. When matter collapses into a black hole, its physical details vanish from view. For decades, that seemed to imply information might be destroyed. But research increasingly indicates the opposite, that the total informational content is preserved, encoded perhaps on the black hole's boundary itself. This is closely tied to the holographic principle, which proposes that all the information about a region in space can be described on its surface. Physicists even use concepts like the Bekenstein bound to quantify this idea, showing that the maximum information capacity of a region scales not with its volume, but with the area of its boundary. This connection between space, entropy, and information hints at something very concrete. Information has physical limits and measurable consequences. Shifting to this perspective forces us to rethink older mechanical models of the cosmos. The classical view treated particles as tiny, solid objects moving like billiard balls across a cosmic table. But quantum mechanics showed that such a picture is incomplete. At small scales, particles are not rigid pieces of matter but probability distributions, constrained by rules of superposition and entanglement. And those rules themselves are best described not as movements of miniature objects, but as transformations of information. Quantum equations read almost like instructions for updating a system's informational state. The probabilities adjusted, the history recorded, nothing lost. This helps explain why quantum technologies feel so different from classical machines. A quantum computer doesn't simulate the behavior of particles as objects. It directly manipulates informational states at the most fundamental level. Qubits can overlap, interact, and recombine in ways that mirror how nature itself operates. Experiments in 2025 showed such systems scaling beyond a few dozen qubits toward hundreds, revealing how quickly informational complexity grows when it is not bound by the strict either-or constraints of classical mechanics. The machines being built now don't just use the rules of physics, they expose them. Seen in this light, everyday matter takes on a new character. The rigidity of a table or the warmth from a stove isn't simply matter behaving mechanically. It's the expression of stable informational arrangements on a macroscopic scale. The patterns of molecules, the bonding of atoms, the flow of heat, all of it results from the way information has been stored and structured through countless prior interactions. Even the apparent emptiness of space may be dense with informational encoding, its vacuum fluctuations reflecting hidden processes running beneath visibility. This perspective invites a shift in how we define what is basic. The proton, the photon, the gravitational field, these may not be the deepest building blocks after all. They may be emergent expressions of a more fundamental substrate, information. What feels like solidity or the flow of energy could simply be the display layer of an underlying computation. In that sense, the familiar world is not an illusion. It's the interface through which informational processes appear to us. When researchers first spoke of the universe as information-based, many heard the comparison as poetic metaphor. But as measurements tighten and theories expand, the metaphor blurs into literal description. Information is not just a label that humans apply after the fact. It behaves like a constrained, conserved element of reality that obeys measurable limits. Many physicists now treat it alongside mass, charge, and energy as central to the accounting of the universe. This shift does not replace the old physics so much as extend it, pointing to a deeper lawfulness beneath the surface. And with this recognition comes a sobering implication. Physical reality might be structured more like a process than a machine. Instead of thinking in terms of parts pushed and pulled, it may be more accurate to think in terms of distinctions updated, records preserved, and informational states transformed. Rather than gears turning in a clockwork universe, reality may operate more like a continuously running program. Its visible outputs the material events we measure, its hidden workings the calculations we can only infer. This idea prepares the ground for the next step. If reality is ordered around informational updates, we need to ask how those updates happen. What kind of logic governs the transitions from one state to another? Classical physics provides one kind of answer, rooted in deterministic outcomes. Yet quantum physics points to another, stranger system of rules that resemble the operations of computation but resist the definiteness of classical machines. The question is whether those rules reveal the true code shaping reality itself. The code of the universe, quantum logic versus classical laws. Classical computers operate on a clear principle. They move ones and zeros through circuits, applying fixed instructions that always resolve to a definite outcome. Every operation is like pressing a switch one way or the other. This binary model has powered everything from smartphones to space travel, but it remains a simplification. Nature at its most fundamental level rarely gives such neat answers. What we observe in the quantum world is filled with uncertainty, overlapping possibilities, and correlations that resist being reduced to tidy categories. This is why quantum computers, though they appear strange at first glance, feel so closely aligned with how the universe already functions. They don't just process information differently, they process it in a way that mirrors the behavior of physical reality itself. In these machines, the fundamental unit of information is the qubit. Unlike a classical bit, fixed as either 0 or 1, a qubit can exist in a mixture of both states simultaneously through a principle known as superposition. If a classical bit is like a coin that has landed heads or tails, a qubit is like holding the coin in mid-spin, where all possible outcomes are still present. The mathematics of quantum mechanics allows calculations to unfold across these possibilities at once, with a definite outcome appearing only when the system is measured. This may seem counterintuitive, yet it is consistent with how electrons, photons, and atoms behave. Superposition, however, is not the only feature that sets quantum logic apart. Quantum systems also make use of entanglement, an effect that standard computers cannot reproduce. When two qubits are entangled, their states are joined so tightly that a change in one is reflected in the other instantly, even across vast distances. No signal is sent between them. Instead, their shared description encodes the correlation directly. Einstein once dismissed it as spooky action, but repeated experiments have established it beyond doubt. Entanglement is not just an oddity, it is a resource. In technology, it enables qubits to coordinate at levels far beyond what separate bits could ever achieve. In physics, it may even play a role in the very structure of spacetime itself. Either way, the lesson is similar. The universe at its core operates through linked outcomes, not isolated events. This parallel between physics and technology raises an important question. Why should the rules that make quantum computers viable line up so closely with the rules that describe nature? Classical computing is a human invention, built on human choices. Quantum computing, by contrast, takes its operating principles directly from what experiments with matter revealed. The probabilistic way these devices function was not imagined, it was observed. Building a quantum computer is not like forcing the world to behave according to our models. It is like constructing a system that runs on the same principles reality already uses. Each demonstration of a quantum algorithm that outpaces a classical one carries technological meaning, but it also signals something deeper. The logic of nature is computational. The differences stand out more when compared side by side. In a classical computer, flipping a bit erases its previous state. The information is lost, like chalk wiped from a board. In quantum systems, prior information lingers within superpositions and entangled states even as they update. This mirrors how physics treats information itself, where evidence increasingly suggests nothing is ever truly destroyed. Energy may transform, particles may scatter, but information seems conserved. Quantum processors echo this by allowing data to interfere with itself in structured patterns no traditional system can imitate. They do not discard states, they preserve and recombine them. Probability further distinguishes the two logics. Classical programs guarantee the same output every time when given the same input. A quantum program instead provides a range of possible results, distributed according to precise mathematical weights. This directly reflects physical experiments, such as observing electrons hitting a screen. You can predict the overall statistical pattern, but never the exact placement of one event. Quantum computers turn this seeming unpredictability into a feature, making uncertainty a working part of the calculation. Nature does the same. The very laws of physics are written not as rigid certainties, but as probability distributions shaping what can occur. By 2025, this once theoretical framework is visible in engineered machines with hundreds of functional qubits. Google's Willow processor, operating with 105 controllable qubits, combined with laboratory demonstrations of below-threshold error suppression, shows that superposition and entanglement are no longer just metaphors. They are tools now being used at scale. These advances confirm how close engineered quantum devices come to reflecting the rules physics already follows. Still, it is important to be precise. Quantum processors have not replaced classical ones. They show massive speedups in very specific tasks, especially problems involving vast possibility spaces, but they are not universally superior. The real significance lies in how they highlight the fact that our technology is beginning to exploit the same code the universe runs on. The implications grow sharper as systems scale. Classical computing is still indispensable for everyday calculations, but it operates on premises that ignore the richness of probabilities and connections inherent in quantum logic. Quantum computing steps closer to how reality evolves. When thousands of possible outcomes are tracked together, when entanglement spans hundreds of qubits, the computations begin to resemble not a tool outside of nature, but a managed version of nature's own activity. Each experiment reminds us that classical algorithms approximate reality, whereas quantum logic seems to embody it. This matters beyond the lab. The things classical logic fails to fully capture, the stability of atoms, the coherence of wave functions, the strange persistence of entanglement, are all explained naturally within the rules that quantum devices are built to obey. The fact that researchers can manipulate these effects rather than just describe them suggests that reality and computation are bound by the same constraints. Our machines are not simply interpreters of hidden laws. They are participants, playing out those laws in engineered form. Seen this way, quantum processors are more than advanced tools. They may be small-scale demonstrations of the very same informational logic that spans from subatomic particles to galaxies. They rely on coherence, correlation, and probability, not certainty. And every time a specially designed quantum program demonstrates results beyond the reach of classical algorithms, it points to the possibility that the cosmos itself runs on similar operating principles. Progress in the field shows how quickly this analogy moves toward practicality. With larger, more stable systems, the boundaries between what is engineered and what is natural continue to blur. Each improvement reflects reality back to us in more detail, as if scaling up processors is akin to scaling up our ability to model pieces of the universe from the inside. The closer these devices get to representing physical processes with fidelity, the less they seem like computational novelties, and the more they resemble windows into how existence processes information. This trajectory sets the stage for the next leap forward. Once quantum machines begin working with thousands of stable, coordinated qubits, they do more than handle bigger datasets or faster searches. They begin to approximate the scale of complexity required to represent patterns within the natural world itself. And it is at this point, as designs push past thresholds long thought years away, that the resemblance between quantum processors and the universe's own structure becomes much harder to dismiss. IBM's 1,000-plus qubit leap and what it reveals. In late 2024 and into 2025, IBM announced a step that the field of quantum computing had been anticipating for years: the achievement of more than 1,000 functioning physical qubits on a single device. Their Condor processor, unveiled at the end of 2023, contained about 1,121 physical qubits, marking the first time a system crossed that benchmark. It is important to be precise here. These were physical qubits, the raw building blocks that hold quantum states. They are not yet the error-corrected logical qubits that researchers ultimately aspire to build. Those remain a future goal. Logical qubits are stabilized, fault-tolerant units that can perform long computations reliably, and scaling them into the thousands is still on the horizon. But even so, surpassing 1,000 physical qubits is a turning point, because it shows that densely packed and controllable arrays can function on a scale large enough to explore problems far beyond toy models. IBM has been careful to emphasize this distinction in its roadmap. Alongside Condor, the company introduced the Heron processor with around 156 qubits, designed not for sheer count but for lower error rates and improved reliability. The lesson was straightforward. Bigger arrays matter, but stable and error-resilient designs are essential for useful computation. IBM's forward-looking plans, such as its proposed Starlink systems in the late 2020s, focus on combining these approaches, using error correction methods like quantum LDPC codes to build genuinely fault-tolerant machines. This makes clear why passing 1,000 physical qubits is both impressive and preliminary. The milestone demonstrates feasibility, but the long-term target remains logical qubits that can sustain calculations without collapsing under noise. Why does this matter so much? Because in quantum systems, scaling has an exponential effect. Adding qubits is not like adding extra horsepower to a car engine. In classical machines, doubling computational parts means roughly doubling performance. In quantum machines, each added qubit multiplies the possible states the system can explore simultaneously. Just 2 qubits hold 4 states, 10 qubits describe over 1,000, and at the level of 1,000 qubits the state space is unimaginably vast. This explosion of combinations mirrors the complexity encountered in natural systems, whether in molecules, stars, or networks of neurons, where rich correlations appear when certain thresholds are crossed. IBM's Condor Leap opened a foothold into that terrain, not by analogy, but by scaling technology into ranges where entanglement and interference start to resemble naturally occurring patterns. The debate about usefulness versus fragility has surrounded quantum computing for decades. Early critics argued these machines would remain too unstable ever to outperform classical systems in practical domains. Yet engineering has repeatedly shown ways to stretch coherence further, extending how long qubits can remain intact before noise overwhelms them. Layering error suppression and correction onto physical arrays begins to yield stability that lasts long enough for non-trivial computation. This is significant beyond engineering. It hints at the same kind of order that physical law itself seems to maintain across cosmic scales. The IBM device does not prove that reality computes, but it narrows the gap between laboratory quantum information processes and the physical behavior we study in nature. The resemblance is worth noting, not as a claim of equivalence, but as a reminder of how closely our tools now echo the operations of the systems we seek to understand. This raises questions about what we really mean when we say a quantum computer represents part of reality. For basic simulations, say, modeling a few molecules, dozens of qubits suffice. More qubits expand the reach into complex materials, superconductors, or catalysts. At the 1,000-qubit threshold, researchers can begin experimenting with highly intricate chemical reactions or the exotic energy states of unusual matter. These are not just demonstrations of speed. They are attempts to recreate, on hardware of our own making, the informational processes that reality itself performs continuously. It is not a simulation in the graphic sense of rendering images on a screen. It is computation itself playing out under the same rules that operate in the universe. That sense of overlap can be unsettling. Why should the engineering of large quantum processors so closely parallel the structures and strategies nature seems to employ? Adding more qubits, correcting for more errors, linking more systems together, all of it feels less like inventing a new paradigm and more like rediscovering one already present. A classical machine is bound by designs of human logic, built around binary switches and deterministic flow. A quantum device with 1,000 qubits aligns itself with probabilities and states that nature itself allows. Every additional scaled unit feels like a further step into the same architecture the universe has been using since its earliest moments. Significance can also be seen in the practical research areas now opening up. Stable arrays of this size make it possible to explore high-temperature superconductivity, where predicting how electrons pair could transform energy transmission. They allow direct modeling of quantum phases of matter that classical simulators can only approximate weakly, and they enable researchers to test aspects of black hole information physics by encoding processes too complex for ordinary computation. These are not only engineering challenges, but also fundamental physics questions. By handling them, quantum computers act as controlled instances of universal rules, a compact stage where theories about the most difficult puzzles can be tested. This does not mean the IBM system or any of its successors are literal universes. They do not replace the cosmos, nor do they prove cosmology's deepest claims. What they do is collapse metaphor into experiment. They show that scaling quantum information processors to new heights produces structures that share striking similarities with the informational architecture we suspect governs space, matter, and energy at base. This milestone suggests that studying such devices is not just about building better computers, but about glimpsing patterns that may already underlie existence itself. Each step closer strengthens that connection. Moving from a handful of qubits to hundreds was one story. Moving past 1,000 is another. At this scale, what began as an engineering project begins to brush against questions usually reserved for philosophy and physics. Why does scaling produce landscapes of entanglement so reminiscent of natural order? Why do era-resilient designs echo the stability we observe in stars maintaining balance over billions of years? These questions remain open, but they remind us of how advances in computation are also advances in how we perceive reality's operating principles. The IBM achievement demonstrates that quantum machines are leaving the realm of laboratory curiosities and moving into practical platforms for physics itself. It suggests that the act of building and scaling them is a way of participating in the same logic that the universe runs on, though in a miniature, controlled form. Whether we see them as advanced tools or as narrow windows onto nature's own style of computation, their importance is hard to overstate. And this sets the stage for another, deeper puzzle. If qubits can mirror some of the structures of the cosmos, what about the invisible relationships that seem to stitch the fabric of reality together in the first place? It is here, when we examine how correlations link across space itself, that we encounter a phenomenon many physicists believe may hold the key to why the universe has structure at all. Entanglement, the invisible threads of space. At the smallest scales of physics, one feature stands out as both strange and essential. Entanglement, the invisible bond that allows particles to share a state no matter how far apart they drift. When two particles are entangled, measuring one immediately tells you something about the other. The unsettling part is that this correlation persists even across large distances, where no signal should be able to travel quickly enough to account for it. Entanglement does not seem to weaken with separation, at least not in the way classical expectations would suggest. Instead, it operates outside the normal rules of space and time that we are used to. Experiments have confirmed this countless times. Photons shot in opposite directions display correlations too exact to be explained by hidden variables. Electrons set into distinct traps behave as if they are still connected, their measurable states lining up as though information flows between them. No classical description can quite capture this. These repeated results suggest that entanglement is not some fringe curiosity, but a basic part of how the universe functions. Some researchers now propose that the connections we observe do not travel across space. They define the fabric of space itself. That claim requires caution, however. It is not that scientists can assert with certainty that entanglement generates spacetime directly. The idea is better described as an active area of research, where evidence and theory point towards space being emergent from deeper informational rules. One way physicists explore this is by modeling entanglement networks mathematically. Individual entangled particles can be represented as links, and when these links scale outward, they form webs that resemble lattices or fabrics. From these webs, large-scale geometry appears to take shape. Theoretical work, particularly through tensor networks such as MERA, multi-scale entanglement renormalization ansatz, has shown how specific patterns of entanglement can mathematically produce spatial geometry. In this view, entanglement is not just a quantum oddity, but potentially the glue binding spacetime together. This doesn't prove the model is final, but it demonstrates in concrete terms how informational patterns could underlie what we experience as distance, shape, and curvature. A single metaphor is helpful here. Imagine a woven fabric. To our eyes, it looks like a seamless surface, but on closer examination, we see the structure, strands crossing and knotting together into a coherent whole. Without the individual threads, no surface exists. With them, texture and continuity emerge. If spacetime behaves like that cloth, then the continuous geometry we perceive is nothing more than the macroscopic effect of countless entanglement bonds at a deeper level. Remove those connections and the very idea of space would unravel. This perspective helps explain why the universe appears so consistent. Light travels through what seems like continuous fields, gravity bends paths predictably, and events unfold in smooth progression. If entanglement organizes space underneath it all, then spacetime stability is a byproduct of those connections. Stronger networks of entanglement might yield rigidity, while weaker or looser connections could give rise to curvature or horizons. Gravity itself could then appear not as a separate force, but as an emergent result of how entanglement distributes and stabilizes information. Again, this is not a settled theory, but research continues to suggest such patterns could underlie the smooth functioning of what we call physical law. What makes this particularly persuasive is how entanglement shows up everywhere we look. It is not confined to exotic physics experiments or abstract models. Chemistry relies on entanglement to hold atoms in molecules. Biological processes like photosynthesis depend on it to move energy efficiently. The quantum computers being built today use entanglement directly to process information across massive state spaces. None of this is metaphor. It is a demonstration that entanglement is a natural rule of physics, one that technology and biology both rely on. This strengthens the view that what we see on the cosmic scale may simply be entanglements reach extended across far larger networks. If this is correct, then our normal sense of distance could be misleading. Points that appear far apart when measured with a ruler might be adjacent within the hidden lattice of entanglement. Likewise, two regions that sit side by side in ordinary space might in fact have very weak ties, making them informationally remote. The implications are significant. What we call space could be less real as a standalone thing and more of a projection of these informational relationships. What appears empty could actually be dense with underlying structure. Time may also need rethinking under this picture. If geometry is produced by entanglement webs, then time could emerge from how those webs update. Each reconfiguration would represent a step forward, like a system refreshing itself continuously. What we experience as moments passing may be the network reorganizing states across itself. Instead of an arrow of time imposed from outside, the forward flow might be the cumulative result of entanglement, links shifting and recalibrating. A computer program, after all, does not move. It executes line by line. The universe may compute forward in much the same way. Considering this, the long-standing challenge of unifying quantum mechanics with gravity takes on a new shape. If gravity comes from geometry, and geometry arises from entanglement, then gravity itself may be better understood as an emergent property of information. In this formulation, no additional force is required. The pull toward Earth or the bending of light near massive objects could simply reflect how entanglement threads knot and tighten. In regions of extreme density, like black holes, the structure of these entanglement configurations might create the horizons and boundaries we observe. These ideas remain highly theoretical, but they offer a bridge over one of physics' most difficult divides. It can be tempting to compare this to familiar human-built networks. The internet, for example, links computers across the globe. To the casual observer, information moves instantly between locations separated by vast distances, but beneath that appearance lies a web of connections and routing paths. Entanglement might provide something similar, but without wires, satellites, or any infrastructure. The connections asterisk are the structure, and no hidden medium is required. This is not a perfect analogy, but it helps capture the idea of an invisible system producing outcomes that, from our perspective, appear impossible. Taken seriously, such a framework forces us to reconsider the status of both distance and separation. Space may not be a stage where physics unfolds, but a property that unfolds because of underlying informational ties. Entanglement does not merely lurk beneath quantum experiments. It could define the way reality itself holds together. This doesn't mean space is fake, in the usual sense of the word, only that our experience of it may be the surface presentation of deeper processes. Physical separation may be a projection we perceive, while reality at its core could always remain linked through unseen connections. And here lies the deeper point. If entanglement functions as the architecture behind what we observe, then it is as fundamental as any particle or field. It acts not like an accessory feature but like the code itself, weaving the environment in which everything else occurs. Where matter appears, where forces seem to operate, how long events unfold, all of these may be surface effects of entanglement networks stabilizing and shifting beneath. This brings us to a broader puzzle. If entanglement can establish geometry, provide stability, and potentially even explain gravity, then what about the parts of the universe that remain stubbornly unexplained? Physics already tells us that most of the cosmos is made up of something invisible, dark matter and dark energy. If entanglement provides a hidden structure for space, could the unseen mass and energy filling the sky also reflect hidden aspects of how the universe processes its information? That question draws us into one of the biggest mysteries of all. Dark matter and dark energy as the universe's processing cost. For more than a century, astronomers have known that the visible universe, the galaxies, stars, planets, and gas clouds we can observe, constitutes only a small fraction of what is actually present. Measurements of galactic rotation, gravitational lensing, and cosmic expansion consistently show a mismatch between what we see and the forces at play. Ordinary matter made of atoms accounts for only about 5% of the total. Roughly 25% is attributed to dark matter, inferred from the way galaxies rotate too quickly to be held together by visible mass alone. Another 70% is labeled dark energy, an unseen driver of cosmic acceleration. Together, these two unknowns make up 95% of the cosmos, yet neither has ever been directly detected. They do not radiate, scatter, or interact like familiar particles. In simple terms, most of reality appears invisible. Traditionally, physicists have approached these mysteries by treating them as missing physical ingredients. Dark matter was cast as an undiscovered particle, perhaps heavy and weakly interacting, or ultralight and wave-like, while dark energy was seen as either a cosmological constant or a new force stretching spacetime. These remain dominant views, supported by vigorous searches. Still, a number of researchers have begun to explore more unconventional possibilities. One hypothesis reframes them not as undiscovered particles or exotic fields, but as side effects of information processing on a cosmic scale. In this view, the so-called dark sector might represent the overhead cost required to keep the universe coherent, an unavoidable expenditure in the execution of reality itself. The analogy emerges when we compare astrophysical puzzles with the workings of quantum devices. In a large-scale quantum computer, most of the system's resources are not devoted to the visible computation, but to maintaining stability through error correction. Vast numbers of qubits operate only as redundancy, silently ensuring that the small fraction of logical qubits can function without collapsing. The visible output depends on a hidden infrastructure that consumes greater capacity than the task itself. Applying this lens outward, some theorists ask whether dark energy represents a similar kind of overhead. Its role would not be to propel galaxies by an external push, but to preserve the stability of universal information as it updates continuously. The accelerating expansion might then be an indirect sign of this hidden processing cost. This is speculative, but it provides a frame for understanding why so much of the universe seems invisible yet influential. Dark matter can be cast in equally informational terms. Observations show galaxies rotate faster than visible mass should allow, suggesting unseen scaffolding that binds them together. Instead of discrete particles drifting invisibly through space, one alternative is that this scaffolding is informational, structures that store and preserve the record of cosmic states across scales. Just as a computer relies on memory registers to stabilize its processes, the universe may rely on a vast reservoir that never appears directly, but ensures gravitational systems retain coherence. In that framing, dark matter is less a missing particle cloud and more a structural necessity of computation. Framed this way, the question shifts. Rather than asking, what are these made of, we ask, why does the universe need invisible resources to keep running? As with any computation, the visible output depends on non-visible costs, power consumption, memory allocation, redundancy. To observers within the system, those costs are not seen directly, but their effects are unavoidable. This is a provocative hypothesis, not a resolved theory. Still, it resonates with current data in intriguing ways. In 2024, the Dark Energy Spectroscopic Instrument, DESI, released results suggesting that dark energy may not be constant, but could evolve over time. That possibility directly challenges the idea of a fixed cosmological constant and opens space for models where the energy density is dynamic. Related research has explored holographic dark energy, HDE, frameworks, where information-theoretic ideas are used to describe cosmic acceleration. Some of these holographic models, including interacting holographic dark energy, IHDE, attempt to link dark energy behavior with information bounds and horizon physics. These are exploratory directions, but they show why new interpretive frames, like treating dark energy as a processing cost, are timely. The old picture of a simple, unchanging background pressure is no longer the only option under discussion. Of course, this informational account is not the only explanation, and caution is essential. Mainstream physics continues to investigate dark matter candidates ranging from weakly interacting massive particles to axions to ultralight scalar fields. More complex scenarios, such as inelastic dark matter, propose that hidden sector particles interact with each other in ways that evade detection but match certain anomalies. These proposals remain active, testable hypotheses guiding major experiments. Any claim that unseen matter and energy are purely computational overhead risks overstating current evidence. At best, the information processing picture offers a metaphorical but structured lens to think about why such a large fraction of the universe remains hidden. The strength of the metaphor becomes clear when we revisit engineering lessons. IBM's Qubit systems, surpassing 1,000 physical qubits, visibly demonstrate that overhead dominates. Most of the machine's architecture is consumed not in performing direct tasks, but in making those tasks survivable. In a cosmic analog, the majority share of hidden energy and mass would not be an error or missing element. It would be expected. From this angle, the 5% of visible matter looks less like the whole universe and more like the small output of a much larger underlying system. Yet it bears repeating that this is a hypothesis, not a conclusion. Presently, no empirical evidence shows dark matter or dark energy are processing costs. The most accurate statement is that this reframe aligns with certain data trends and metaphors drawn from computation. Future surveys like DESI, Rubin, and Euclid will provide critical tests. If dark energy evolves in line with holographic or dynamical models, informational interpretations may gain strength. If it proves static, the cosmological constant remains a strong fit. Either way, observational progress will decide whether these crossovers between computer science and cosmology belong within mainstream theory or remain philosophical analogies. Still, even as metaphor, the idea shifts how we think about the enormity of hidden reality. 95% of the universe as invisible overhead sounds less implausible when placed next to the ratios inside functioning quantum devices, where redundancy outweighs visible calculation by orders of magnitude. It suggests that absence in measurement does not imply absence in function. What is unseen might not be missing, but operating beneath the visible layer as essential support. In this framing, the dark sector no longer poses the paradox of substances that defy detection. Instead, it represents the unseen substrate without which the visible universe would lose coherence. If galaxies hold together, if spacetime expands smoothly, perhaps those observed patterns are the emergent evidence of hidden informational scaffolding. Such an outlook emphasizes not just what we cannot measure, but why invisibility itself might be integral to the whole system. And if dark energy and dark matter are best approached as unseen structural necessities, then we are compelled to ask where else information might hide. Observations already point us toward phenomena where ordinary models break down, such as black holes. Those extreme regions concentrate mass and warp space to a degree that resists explanation, leaving open the question of how information persists when matter falls beyond the point of no return. Whatever dark matter and dark energy ultimately prove to be, exploring these gravitational enigmas draws us closer to the connection between information and the very fabric of reality. The holographic principle, reality projected from information. Black holes have long exposed one of the toughest contradictions in physics. According to general relativity, once something crosses their event horizon, no light or signal can ever escape. A star collapsing inward, particles spiraling into the core, everything is hidden, seemingly gone forever. If that were true, it would mean the universe allows information to be destroyed. But quantum theory insists that information cannot vanish from the universe. Those two descriptions, both powerful and well-tested, clash directly when applied to black holes. The conflict sharpened in the 1970s with Stephen Hawking's discovery that black holes radiate energy very faintly, through what became known as Hawking radiation. This showed that black holes are not permanent, they slowly evaporate. Yet that deepened the paradox. If a black hole disappears completely, the information it swallowed appears lost forever. Reconciling this required a new framework, one that preserved quantum conservation while respecting relativity's geometry. One of the most influential proposals reframed the event horizon itself as an information surface. Rather than being a one-way point beyond which data is destroyed, the horizon could be a storage layer where every detail about infalling matter is imprinted. In this picture, a black hole does not wipe its past clean. Instead, it compresses three-dimensional details into a two-dimensional record written on its boundary. This insight gave rise to the holographic principle. In concise terms, everything contained inside a region of space can, in principle, be described entirely by information encoded on its boundary. Just as a physical hologram projects a 3D image out of a flat plate, the principle suggests that the fundamental data of a region may lie on its surface. The Bekenstein-Hawking entropy relation, which links a black hole's surface area rather than its volume to its informational content, was the seed for this idea. At first, holography was viewed narrowly, as a tool to resolve black hole paradoxes. But as theorists explored its consequences, a more daring possibility emerged. If black holes safeguard information on their surfaces, perhaps space itself functions the same way. What we perceive as depth may not be fundamental at all, but emergent from data at boundaries. In this sense, three-dimensional reality might be better understood as a form of projection from lower-dimensional encodings. It is important, though, to mark the limits of this claim. Some researchers model regions of spacetime holographically using the AD-SCFT correspondence, a powerful mathematical duality between a gravity theory inside a negatively curved bulk and a conformal field theory on its lower dimensional boundary. AD-SCFT has delivered strong evidence that holographic equivalence works in certain geometries. Expanding this approach to cosmologies like our own, which appear closer to de Sitter space than anti-de Sitter, is active but technically challenging work. So while holographic models are compelling, it is more accurate to say they provide promising tools rather than a final description of our universe. In 2025, new studies pushed this further. Several groups applied ideas from quantum information, exploring how horizons function like advanced error-correcting codes. The results showed that data falling into black holes does not vanish, but is distributed redundantly across boundary surfaces, protecting it much like digital codes shield information from loss. In May 2025, researchers also proposed fresh ways to test holographic predictions in controlled systems, including cold atom setups and mathematical checks against quantum field calculations. These efforts underscored that holography is not just speculative metaphor. It is a framework generating testable predictions that scientists are actively probing. The encoding itself has surprising properties. In digital systems, redundancy ensures a message can be recovered even if pieces are corrupted. Boundary storage in holography seems to perform an analogous function. No single point at the edge contains the full record. Instead, information is smeared across the entire horizon so thoroughly that damaging part of it does not erase the whole. This makes black holes look less like destructive agents and more like stable archival devices. Theoretical work using tensor networks demonstrates how such distributed encoding can generate consistent interior geometry. Entanglement patterns stretched across the boundary reconstruct a sense of depth. Space may appear inside because information is so skillfully organized at the edges. Holography also ties separate theoretical puzzles into one frame. Black hole entropy becoming proportional to surface area, a strange result at first glance, now looks expected. Information conservation, once at risk of collapse in gravitational contexts, finds a natural safeguard. Even the behavior of quantum fields resonates with holographic correspondences, implying that particle interactions may emerge from lower dimensional encodings. What bridges them all is a consistent principle. Boundaries hold the record, and what looks like interior complexity results from projecting that record inward. Skepticism remains, and rightly so. Transforming this principle into a faithful description of our expanding universe is not trivial, yet its strength is clear in how it unites mathematics across gravity, thermodynamics, and quantum theory without contradiction. 2025 studies showed holographic calculations producing outputs aligned with predictions from both relativity and quantum field models. That convergence grants weight to the idea, even though it remains unproven. For human perspective, the implications are striking. If holography holds, then space may hold less raw descriptive content than it seems. Instead of scaling with volume, the information describing a region scales with surface area. What feels endless might in principle be contained by limits far smaller than intuition suggests. Black holes in this frame swap roles from engines of destruction to keepers of record, preserving history at their horizons long after their contents fall in. The grand expanse of three-dimensional space would not be an illusion. It would be a lived reality emerging from deeper informational architecture. A useful comparison lies in how holographic images work. When light strikes a flat holographic plate, the image that appears floats in 3 dimensions, but all the detail is coded onto a 2-dimensional sheet. Destroying part of it degrades the image, yet the full picture often remains recoverable from the surviving surface. Replace the plate with a cosmic boundary, and the projected image becomes our experience of depth, distance, and matter. The world we walk through is no illusion, but it may be sustained by patterns we cannot normally see. That line of reasoning changes what it means to ask whether information is destroyed. From a holographic perspective, the answer is no. Information is always stored, but not where we expect. The question shifts from does it survive to where is it encoded? Each photon absorbed, each particle interaction, each collapsed star might already be inscribed somewhere at the boundaries of reality. As this principle matures, it also connects back to the practical domain of quantum technologies. just as experimental processors spread data redundantly across many fragile qubits to preserve it. Holography implies nature employs similar protective schemes at cosmic boundaries. The link may not be accidental. Holographic descriptions begin to look like the universe's own way of ensuring robust information storage amid chaotic processes. And if space and matter truly arise from boundary encodings, then the most pressing question becomes how that encoding resists breakdown. Quantum entanglement appears central, distributing information so that no local interruption can erase it. This redundancy resembles a hidden protective layer woven into the structure of the universe itself. It suggests that the smoothness and consistency of reality may depend on the same kind of safeguard physicists struggle to engineer in quantum computers. That opens onto the next challenge. If holography is accurate, we still need to understand the mechanism that guarantees such stability. How does the universe maintain coherence of its information across billions of years, despite fragility at quantum scales? This puzzle pushes us toward the idea that reality carries within it something like a built-in safeguard, a code designed at the deepest level to preserve information against collapse. Quantum systems are notoriously unstable. A small disturbance is enough to break superpositions, collapse entangled states, or erase fragile information. Researchers working with qubits are reminded of this every day. Stray heat, background noise, or even a single photon striking at the wrong moment can scatter the computation and destroy coherence. Because of this, working quantum computers require elaborate protection. They cannot function without error correction routines that distribute information across multiple qubits so that local failures do not wipe out the encoded state entirely. Against that backdrop, one puzzle remains. If individual quantum systems are this vulnerable, how does our universe itself, built on quantum processes, sustain consistent order across billions of years? One possible answer has been taking shape. Recent theoretical work indicates that spacetime may not simply be a neutral stage, but could function like an error-tolerant system, encoding information redundantly across extended networks. Instead of holding data in one fragile state, the universe could spread and overlap information across many links, allowing local loss to be corrected by the system as a whole. This idea, that reality preserves its structure by functioning like a massive quantum error-correcting code, emerges not only from metaphor, but from explicit models connecting error correction with holography and add-SCFT. In fact, researchers have shown that the mathematics used in holographic dualities maps directly onto quantum error-correcting codes, suggesting redundancy is a built-in feature of the way geometry itself operates. Engineered quantum computers provide a helpful reference point. To create a logical qubit, the kind needed for meaningful, stable computation, engineers do not rely on a single raw qubit. They bind together many fragile physical qubits into a collective state, woven by correlations that protect the encoded information. Even when some of the individual components fail, the redundant structure allows information to be recovered. The trade-off is cost. Many qubits serve purely as scaffolding in order to safeguard a single logical one. The resemblance to the universe is suggestive. If reality functions like a computation, it too may require a safeguard against error, an architecture that distributes information so broadly that no single failure can erase it altogether. In this view, cosmic stability is no longer paradoxical. Photons from the early universe continue to carry imprints of their origin after traveling for more than 13 billion years. Entanglement correlations are observed across astronomical distances. Instead of treating this as an improbability, redundancy offers an explanation. Information is never purely local. It is distributed widely enough that local decoherence does not erase global records. Failures at one node do not collapse the system because recovery is always possible from the broader network. This interpretation extends naturally from the holographic principle. If the surface of a region holds the information about its interior, then those boundary encodings may operate in ways familiar from error correction. Studies in the last decade have demonstrated that holographic mappings between bulk geometry and boundary field theories can be cast explicitly as quantum error-correcting codes. In these mappings, the same information can be reconstructed from different boundary regions, mirroring how redundancy protects against corruption in quantum devices. This is not simply an analogy. Models show that the very mathematics used to describe spacetime structure aligns with the mathematics of protecting information through code-like architectures. From everyday perspective, this could explain why physics appears relentlessly durable. Atoms remain stable because their underlying quantum states are not left fragile and unprotected. They are embedded in a network that corrects transition errors. Chemistry, planetary motion, and conservation laws act like repeating correction routines that restore consistency when interactions threaten to deviate. In computer science, error correction ensures that noise is distinguished from signal. In physics, the laws themselves may function like universal recovery algorithms, guarding the coherence of reality against perturbation. The problem of locality also finds a possible answer here. Normally, we think events are restricted to local influence. Cause at one point produces effect at a nearby point. Yet quantum entanglement reveals correlations across distance that resist explanation within this framework. Error correction suggests that such non-local consistency does not imply signals traveling faster than light. Instead, outcomes are restored across a distributed system. The code already spans the regions involved, so updates reflect consistency requirements rather than long-range communication. Correlations emerge not from transmission, but from redundancy built into the shared fabric. Recent contributions reinforce this perspective. Work in 2025 extended earlier tensor network models, showing how entangled webs of correlations can generate spacetime geometry that also functions as a code. Tampering with limited parts of the network failed to destroy encodings, since information could be reconstructed from surrounding regions. This looks structurally identical to how known error-correcting codes, like QLDPC codes, operate. In physical terms, it suggests that the shape of space expresses where redundancy resides. Geometry may itself be the arrangement of information distributed to prevent corruption. These theories gain further credibility from concurrent engineering progress. Companies such as IBM and Google have identified advanced error correction as the key barrier to building useful quantum computers. Current efforts focus on implementing quantum low-density parity check, QLDPC, codes, which promise lower overhead while maintaining robust protection. IBM, for instance, released a preprint in 2024 outlining progress towards scalable QLDPC codes and included them in its roadmap for fault-tolerant machines. Demonstrations of early logical qubits have already been achieved in labs, showing that distributed protection is not abstract. It is the exact method by which machines achieve reliable computation. The convergence here is noteworthy. The same principle, redundancy through carefully structured codes, appears as both a path toward working technology and as a possible universal mechanism underpinning cosmic stability. From this angle, the persistence of order in the cosmos is not a matter of chance. What seems like fragility at the laboratory scale, particles decohering almost instantly, owes to their disconnection from the wider structures that maintain resilience. In the universe as a whole, particles and fields are never fully isolated. They are interwoven into a global error-protected system where information loss at one point is absorbed and corrected by the rest. What local perspective calls unstable, global perspective recognizes as inherently safeguarded. The comparison with our engineered devices then becomes revealing. Every time researchers cluster physical qubits into stable logical units, they copy, in miniature, the strategy the cosmos itself may employ. Where human-built systems fight fragility at small scales and brief timescales, nature shows that the same approach can be executed at astronomical scales and sustained across billions of years. In that sense, technology is not creating this principle but uncovering it, mirroring on small, imperfect stages what the universe seems to do at full capacity. This outlook reframes how we perceive the foundations of law and structure. If error correction lies at the core of reality, then the universe is not best described as fragile matter clinging to existence, but as a process constantly preserving itself. Laws of physics become less like imposed external commands and more like the operational routines of a code built to survive. The constancy of order is not an unexplained given. It is the outcome of an active safeguard that has operated since the universe began. Still, it is important to recognize nuance. Saying the universe is a quantum error-correcting code goes further than evidence supports. A more careful claim is that models connecting holography, entanglement networks, and tensor codes indicate spacetime could behave like an error correction system. This provides one compelling way of explaining why information conservation holds even in black hole evaporation, and why cosmic stability has persisted for billions of years. Whether this description is literal or metaphorical awaits further verification. But the consistency between theory, observation, and laboratory engineering gives it unusual weight compared to speculation alone. If protection through redundancy is indeed this fundamental, then stability is not passive but actively maintained by the fabric of space itself. Structures endure not because they are resistant by nature, but because they are maintained by an underlying process of continual correction. From protons to galaxies, consistency exists because the code that makes up reality requires it. Matter, forces, and time all play roles in that recovery process. The broader implication is that existence does not unfold as a fragile accident waiting to collapse. It continues as a system designed, or at least structured, to defend its own coherence. To put it differently, order survives not in spite of fragility, but because fragility is never allowed to accumulate unchecked. The hidden safeguard ensures history endures, that the informational record written at the beginning of the universe remains accessible, no matter how much time passes. Understanding this changes how we think about the very question of what kind of system the universe could be. If stability is preserved through layers of informational redundancy, then reality may not resemble a machine operated from outside, but a process running from within, a computation whose first obligation is to preserve itself as it unfolds. And it is at this point that another question arises. If the cosmos is not susceptible to collapse because it is continually corrected, how should we understand its relation to ideas like simulations or external programmers? Not a simulation, the computation itself. Simulation theory often captures attention because of its appeal to our technological imagination. The suggestion is simple. The universe may not be the fundamental layer of existence, but instead a complex artificial program operating on some machine beyond our reach. In this conception, reality would resemble a rendered environment like a digital video game, with every law, particle, and observer emerging from instructions written by an outside intelligence. This idea gained traction because it aligns with our current technological metaphors. If human beings already design intricate simulations and virtual worlds, it seems plausible to imagine that a more advanced intelligence could simulate an entire cosmos on unfathomable machinery. If that were the case, matter and energy as we know them would be synthetic, and we ourselves would be artifacts of code. But a growing number of researchers argue that this framework leads to more problems than it solves. The key weakness lies in the assumption at its foundation. If the universe is a simulation, then there must be an external simulator. There must exist an operator, a device, a data reservoir capable of hosting every state we observe. Yet physics has uncovered no sign of such an external layer. Instead, what experiments demonstrate is that information is processed continuously inside the universe itself, governed only by rules we call laws of physics. This alternative, sometimes described as computation as ontology, does not replace reality with a higher machine. It says reality computes intrinsically. Simulation implies an outside host. The computation view says the universe carries out informational updates on its own, with no external programmer required. This distinction matters. A simulation is a recreation. When scientists simulate climate models or planetary orbits, the processes calculated are not real weather or actual worlds. They are approximations carried out within another system. Computation is different. Computation is not about resemblance but about execution. When the universe updates informational states through particle interactions or spacetime dynamics, those updates are not imitations. They are the actual operations that constitute physical reality. The phrase shifts our understanding from imagining reality, running on something else, to grasping that the transformation of information is the reality itself. There are two serious physical objections to the idea of a perfect external simulator. The first is reflexive limitation. A system cannot perfectly simulate itself. Any attempt to host a complete universe must still omit or approximate elements, creating inescapable gaps. The second comes from physics, in particular the Bekenstein bound, which states that the maximum information capacity of a region of space scales with its surface area. This bound sets a hard limit on how much information can exist in a finite region. For an external computer to simulate the cosmos in perfect detail, it would require informational capacity exceeding that of the universe itself, a contradiction. These reasons undermine the plausibility of a larger machine hosting every state of our reality. By contrast, the computation view sidesteps the problem. The universe does not stand in for a model of itself. It operates directly within its own constraints. Such reasoning is supported by specific clusters of evidence. Quantum mechanics demonstrates that information is conserved and encoded in measurable ways. Holography and the association with error correction imply that even extreme gravitational systems preserve records rather than destroy them. Progress in quantum technologies shows that nature handles informational updates at scales still far beyond artificial capacity. Together, these strands reinforce why some researchers find the computational view more aligned with observation than the literal simulation metaphor. The emphasis is not that physicists have reached consensus, but that computation appears to be a more natural description of what the universe is doing, grounded in structures revealed by experiment and theory. This perspective also reshapes comparisons with human technology. In the lab, classical computers simulate quantum states only by approximation, and they fail once entanglement grows past a few particles. Our largest machines cannot track the exponential complexity of the simplest quantum networks, and yet the universe evolves those states fluently at every moment, handling staggering informational loads without hesitation. This asymmetry suggests a difference of category. The universe is not calculating copies of quantum states, it embodies them. Every interaction between particles is a direct execution of informational updates that generate physical outcomes. The connection to redundancy reinforces the point. Quantum computers on Earth require error correction codes to survive norms. They devote vast resources to ensuring fragile states remain intact. Research suggests spacetime shows similar structures, distributing and safeguarding information without any signs of being managed from outside. If this protection were the product of an external simulation, we might expect boundary layers in some higher reality. Instead, safeguards appear woven into the very geometry of space. In a computational ontology, this makes sense. The redundancy does not sit on another platform, but arises as the substance of the universe itself. This contrast also diffuses some paradoxes commonly associated with simulation theory. Searching for flaws in the code, glitches or breakdowns, is often seen as a test for whether reality has been simulated. But physics has yet to reveal anomalies that require external programming as explanation. What experiments yield instead are consistent, probabilistic regularities. Even the oddities of quantum mechanics appear lawful and replicable. Rather than signs of a disguised system, the results align with what one would expect if the laws are the operations themselves. Computation need not conceal imperfections in imitation, because there is no imitation in the first place. Scale offers another reason to favor computation as ontology. The resources needed to simulate every particle interaction would have to surpass the capacity of the observable universe itself. A host machine larger than the cosmos remains a speculation unsupported by evidence. By contrast, if the universe is computation itself, no such external scaffolding is required. Information simply evolves according to the built-in rules. The problem of hosting vanishes, because there is no higher platform necessary to hold the states. Critics of simulation theory emphasize its cultural origins. Each period frames the universe with its most advanced tool. Centuries ago, clockwork mechanisms encouraged a mechanical metaphor. Later, industrial machines shaped how people understood physics. Today, immersive digital systems naturally inspire talk of simulation, but taking metaphors literally can cloud physical clarity. The computation view, grounded in entropy bounds, redundancy models, and quantum processing, relies less on metaphor and more on evidence. The focus shifts from technology's reflection of culture to physics' reflection of reality. It is crucial, however, to avoid equating computation with the machines we build. The universe is not structured like our laptops or phones. Those systems implement computation through silicon, logic gates, and circuits. The cosmos operates probabilistically, through superposition, entanglement, and distributed networks embedded in spacetime. Its updating rules resemble quantum logic far more than the determinism of classical algorithms. But just as an artificial computer tracks states through logical transitions, the universe evolves by shifting informational states in accordance with physical constraints. That function, state-to-state updating, defines computation broadly enough to apply. Under this framework, our own place within the system looks different. If reality were a simulation, then our choices and experiences would be artificial products scripted by an external coder. The computation view discards that outside control. Instead, conscious processes, our thoughts, memories, and decisions, are participants in the universal flow of informational change. Awareness belongs not to an artificial script, but to patterns inside the execution itself. In that sense, beings are regions of the computation aware of their own structure as it unfolds. The immediate consequence is that we are not actors in a fabricated theater. We are portions of the universe operating on its base rules, not approximations run elsewhere. Every neuron firing, every particle drifting, every collision in distant space shares the same foundation. There is no external manager shaping the flow. The continuity we observe is the continuity of the computation itself, progressing moment by moment. Recognizing this reframes what counts as meaningful inquiry. The key is not whether another machine hosts us, but how informational rules generate physical form directly. The emphasis shifts from speculation about hidden programmers to study of redundancy, entanglement, and the laws that govern state updates. Each discovery about error correction or holography thus becomes insight not into a game running on foreign hardware, but into the ontological process that is existence itself. Once this distinction is recognized, it sets the stage for a far more personal question. If matter and energy can be understood as products of informational processing, what are we to make of the patterns we call thought and awareness? Consciousness as a computational output. Thought and awareness can be approached not as mysteries outside of nature, but as processes carried out by the same informational rules that govern matter and space. When neurons fire, ions move across membranes, chemicals exchange signals and electrical impulses arc across synapses, they are not exceptions to physics. They are consequences of it. Beneath the biology lies the same substrate: quantum states updating, particles interacting, and information shifting in lawful patterns. From that perspective, consciousness can be studied as computation made self-reflective, an output generated by physical processes arranged in a certain way. The core question is whether consciousness is only a byproduct of complexity or itself a structured outcome of how information is processed in networks like the brain. Models of information in complex systems suggest one path toward an answer. Conscious experience could emerge at the point where computation becomes recursive, able to represent not only sensory input from the external environment, but also its own internal states. The brain functions in this way. It does not merely register light, sound, or touch. It is constantly computing itself, updating representations of its own condition, integrating memories, adjusting probabilities about future outcomes. This recursive loop creates self-reference, which many cognitive models identify as the basis of awareness. Under such frameworks, consciousness does not require a separate field or a hidden force. It arises when matter becomes organized in ways that encode information about both the world and itself. Consider the contrasting case of a simple circuit that transmits signals in only one direction. Such a circuit cannot become aware of itself, but increase the density and allow signals to loop back, and you create the possibility of feedback. Layers of cycles and returns within the system allow the computation to track its own state. The human brain, with tens of billions of neurons and trillions of connections forming loops within loops, exemplifies this principle. Its complexity enables feedback thick enough to produce the continuity of self we call conscious experience. What has seemed mystical for centuries becomes explainable as information flow weaving back upon itself at a scale capable of reflection. This framework naturally raises the question of human choice. If the universe evolves according to computational rules, do our decisions simply unfold deterministically from prior inputs, in the same way a classical algorithm yields predictable outputs? Many neuroscientists and philosophers argue that if every state follows from the previous one, then free will is no more than the feeling of inevitability in motion. Yet physics at the quantum scale challenges strict determinism. Outcomes are not always preloaded but probabilistic, with possibilities collapsing into specific results only upon interaction or measurement. If brain activity amplifies or incorporates this probabilistic structure, then choices may be better understood not as predestined results, but as real-time resolutions of possible states. In that sense, decision-making could be the subjective experience of a computation that executes step by step, rather than unfolding as a closed script. Experientially, this aligns with what it feels like to choose. We weigh options, experience uncertainty, and resolve into one action. If the brain's probabilistic states are evaluated in layers of simulation before reaching an outcome, then the feeling of agency could be the experiential layer of that calculation. Rather than undermine free will, computation reframes it. We act as processors where probabilities refine into outcomes, and the subjective sense of choice corresponds to the computational process completing its resolution in real time. Consciousness also distinguishes itself through its ability to model hypothetical futures. Rocks, rivers, and stars follow physical rules passively. Conscious beings simulate outcomes internally before acting. The brain, as a biological processor, constantly constructs models of possible actions, calculates their repercussions, and iterates on these before producing behavior. This nested simulation gives rise to imagination and foresight. It is computation operating on its own computations, treating its models as inputs. Consciousness can thus be viewed as the point where the informational process becomes reflective, not only modeling the world but modeling its own act of modeling. At this stage, we encounter an ongoing research divide. Some theorists propose that quantum effects are directly relevant at the level of biology, suggesting that consciousness requires quantum information as part of its operation. Studies have hinted at unusual coherence times in certain proteins, and isotope-dependent responses to anesthetics have been interpreted by some as markers of underlying quantum processes. In 2025, Aniobin Bandiapatié and colleagues argued that networks of tryptophan molecules in cytoskeletal proteins might support biological superradiance, enabling rapid quantum signaling within warm neural environments. But while such results are provocative, they remain controversial. Many neuroscientists, including respected figures like Christoph Koch, argue that strong evidence is lacking and demand reproducible demonstrations before drawing such conclusions. It is useful to phrase the question cautiously. Consciousness plausibly emerges from complex information processing. Whether quantum effects are essential to that process is an open research question being actively tested. In short, some researchers point to experimental leads, unusual quantum behaviors in cytoskeletal proteins or anesthetic isotope shifts, as possible signs that quantum rules contribute to awareness. They suggest that recursion and self-reference in the brain might operate on a quantum substrate. Others doubt this interpretation, emphasizing that neural processes may be explained adequately through classical network dynamics. Both sides agree, however, that consciousness is at least computational in character. It arises when information processing reaches a level capable of integration, feedback, and self-modeling. Whether quantum mechanics plays a fundamental role or not remains unsettled, but the field is moving steadily toward empirical tests rather than speculation alone. Framed computationally, consciousness presents another notable property: continuity across time. Awareness is not experienced as a series of isolated moments, but as an unbroken self stretching across memory and projection. This continuity requires stable yet flexible encoding. Brains achieve this by storing past states in neural patterns and integrating them with current signals in real time. In effect, consciousness overlays present perception with memory, stitching them into a stream we experience as personal history. Time from this perspective is not merely external progression, but the internal computation of past, present, and possible futures into coherent continuity. Moreover, consciousness output goes beyond immediate survival calculation. Human thought creates abstractions, mathematics, languages, and works of art. Each is a second-order product of computation that models itself at more abstract layers. A simple algorithm runs inputs to outputs. The conscious brain builds representations that can describe not only daily stimuli but galaxies, quantum fields, and computational theories themselves. These metamodels are evidence of recursive depth, where thought becomes capable of representing structures with no immediate sensory anchor, including reflection on its own processes. If this interpretation holds, awareness and free will are not illusions, but the form computation takes when it exceeds raw reaction and integrates probabilistic calculation with self-representation. Choices feel real because they are real. They are the outcomes of distributions resolved in feedback loops rather than instructions predetermined to the last digit. Consciousness feels irreducible because it is not reducible to linear calculation. It is the recursive returning of the system upon itself. It is computation folded inward, producing awareness as a structured byproduct of its depth and density. The broader significance is that conscious experience remains consistent with physical law. It does not float outside the rules of physics but emerges from them. It may be rare in the cosmos, but it fits smoothly into the computational ontology suggested by physical evidence. Where matter organizes into biology, and biology organizes into networks dense enough to loop upon themselves, awareness arises. From that view, consciousness is computation's most unusual but lawful product, an echo of universal rules tuned into self-recognition. Understanding awareness in this informational frame reshapes what counts as progress in its study. The task is not to search for hidden substances or external fields, but to measure, test, and refine our understanding of how informational systems become self-referential at scale. Theories that integrate classical neuroscience with quantum tests will either confirm or limit the role of quantum effects, but either result grounds awareness as part of the same ongoing lawful process that governs matter and energy. This opens onto a broader puzzle. If thinking beings are products of this computation, then our own exploration of these questions becomes part of the system's activity. Observers inside the process can construct models of its rules, but must confront the limits of scale and self-reference. That realization ties to a more difficult problem, one that emerges when the computation is asked to account for itself fully. How far can a system extend its own description before meeting boundaries it cannot cross? The future of discovery: can we compute the computer? The question now becomes sharper. What does it mean to study the universe if the universe itself is computation? This brings us to the next challenge. Can we compute the computer? The paradox here centers not just on technology, but on the fundamental limits of physics and logic. If the cosmos is a quantum computation, is there any way to replicate it in full? Or are we restricted to fragments that show us patterns without ever reaching a complete duplication? At first glance, the ambition seems straightforward. We have already built quantum devices that mimic aspects of chemistry, condensed matter, and even simplified models of black holes. If fragments are possible, why not the whole? But the problem emerges quickly. A fully detailed simulation of reality would not only need to approximate fundamental processes, it would need to contain the entirety of the information the universe already holds. That poses a direct contradiction. As the Bekenstein bound shows, the maximum amount of information that can be stored in any finite region scales with its boundary area, not volume. For the universe to contain a perfect simulation of itself, it would need to exceed its own capacity, something no system can do. Here, the principle of computational irreducibility also comes into play. Many processes cannot be compressed or shortcut. They must be executed step by step, exactly as they unfold. A universe cannot sidestep its own unfolding with a compressed copy. This is why physicists stress that quantum computers, while more powerful than classical devices for specialized tasks, are not magical machines that can host entire universes. They can natively simulate limited quantum systems far more efficiently than classical computers, but simulating the totality of existence would require resources on the same scale as the universe itself. Even IBM's roadmap, which presses towards scaling logical qubits through advanced error correction, makes clear the goal is not universal duplication. The aim is targeted: molecular simulations for better drugs, modeling exotic states of matter, and testing small-scale models of extreme physics like those found in black holes. From this perspective, the boundary of possibility becomes clearer. We cannot build an emulator of all reality, but that does not strip the project of power. It simply shifts the strategy. Where totality is impossible, fragments become the method. Physics and computation thrive not through copying everything, but through models that isolate parts of the system, exposing general laws. No cosmologist simulates every atom to understand galaxy rotation curves. They model representative dynamics and extend the results. Similarly, no one needs to compute each quark to test whether redundancy preserves information across spacetime. It is enough to create small regions, analogs of the larger code, that reveal the principle in action. These fragments are already delivering insight. Quantum devices have demonstrated accurate simulations of molecules whose complexity defeats classical computers. Small-scale codes have been used to mimic effective horizons, producing black hole-like behavior in laboratory systems without requiring cosmic mass. Even quantum processors with relatively few qubits can reproduce signatures that echo entanglement structures thought to shape spacetime geometry. Each of these achievements is not a piece of trivia. They are proofs that narrow probes can open windows into laws too immense to recreate fully. The difference between full duplication and fragment modeling is fundamental. A perfect recreation would require a second universe, indistinguishable and unfolding in parallel with our own. By definition, it could not be smaller or simpler than what it represents. Useful models, however, succeed by compression. They shave away detail that does not matter for the phenomenon under study, retaining only the critical features. This is what makes them valuable. Compression is the reason we can forecast weather, predict chemical reactions, or describe stellar formation. Physics is the art of useful loss, discarding unnecessary detail to extract governing rules. The paradox of total simulation carries an ironic twist. Even if it could be done, it would not provide us with answers any faster than the universe itself already provides. A copy of reality running step by step would remain in lockstep with what is unfolding. It would not predict beyond what is happening. It would merely mirror it. This shows why fragment models deliver more insight than any hypothetical perfect duplication. By simplifying, they let us accelerate understanding, foresee outcomes, and uncover structure. The apparent imperfection is their real strength. This reality reframes major milestones in quantum computing. When IBM built Condor with over 1,000 physical qubits, observers were tempted to see this as the beginning of simulating all things. But the actual achievement was subtler and more profound. It represented the planting of tools capable of touching the architecture of reality at new depths. Every additional set of stable qubits offers not the promise of universes in a box, but the chance to probe entangled patterns, redundancy, and probability directly. A fragment of superconducting qubits shows in miniature what the cosmos may be doing at enormous scales. A fragment of digital correction teaches us why reality itself seems resistant to error. These glimpses make progress tangible. Scientists already rely on partial models in other domains. When studying turbulence in air, researchers do not track every molecule. They model sections, extract rules, and extrapolate outcomes. When analyzing planetary orbits, they do not replicate the entire solar system atom by atom. They simplify to the relevant forces. In the same way, investigating whether the universe processes information requires sampling, not total recreation. By simulating representative patches, qubit networks imitating entanglement webs, quantum algorithms tracking exotic matter interactions, we can infer how the larger computer operates. Recognizing these limits signals where genuine progress lies. Just as computational irreducibility means no shortcut bypasses reality's stepwise unfolding, it also clarifies that the best we can do is capture partial views that reveal key dynamics. Searching for shortcuts may be futile, but constructing fragments allows us to test laws directly and repeatedly. The stronger the fragments, whether modeling chemical bonds, condensed matter, or toy black holes, the more confidently we recognize computation as the substrate of reality. This understanding carries an important payoff. The universe cannot be simulated in entirety, but by studying parts, we can identify the rules that generate the whole. Fragmentary glimpses, when repeated and combined, sketch the code from which everything else arises. Each limited experiment scales outward in understanding, pointing to generalities that no total copy would let us see. Paradoxically, imperfection becomes the most efficient path to knowledge. This is why current advances do not represent failure to match the universe, but precision in asking the right scope of questions. When quantum simulators calculate protein interactions unfathomable to classical computers, they move us closer to applying computation to life itself. When small black hole models reproduce evaporation-like signatures, they move us closer to understanding how gravity interacts with quantum rules. These are the fragments that matter. They show that reality is computation not through abstract speculation, but through operational evidence. The important lesson is that pursuing fragments does not diminish our place in the system. It refines it. We cannot separate ourselves and calculate totality from outside. We can only take part within, sampling parts of the process. But that participation is precisely what progress looks like. By working with limited pieces, we learn about the underlying structure governing all, even while the total structure exceeds us. And this brings us closer to the most pressing question. If our tools and theories expose fragments of the cosmic computation, then what does it mean for us, conscious agents, to be embedded in that process rather than outside it? If the universe functions as computation, then meaning does not reside outside the system but emerges from the steps of its operation. We are not separate observers standing apart from it. We are structures within it, patterns of information shaped by the same rules we study. Awareness itself becomes one expression of this ongoing process. The evidence pillars are clear. Information behaves as a physical quantity. Black hole and Bekenstein results set boundary limits. Quantum computing milestones show laboratory access to the same rules, and cosmological studies like DAISY and holographic models make the perspective timely. Yet open questions remain. Future data from DAISY, Euclid, and Rubin will test whether dark energy evolves, and whether holographic encodings describe our universe fully. For now, the most striking fact is this. The cosmos computes, and we recognize it precisely because it computes through us.